All right, guys, I am going to go ahead and get started. So today we're going to talk about derivatives and integrals of vector valued functions, arc length, functions of several variables, and partial derivatives. That's derivatives of functions of several variables. So what does the derivative of a vector valued function look like? How do we define that? Well, if we have, r of t equals f of t for the x component, g of t for the y component, and h of t for the z component, then the derivative of r with respect to time, we define, that's also, aka r prime of t. We have the limit as h approaches 0 of r of t plus h minus r of t over h. So this is actually, I think, on you guys' paper homework to calculate this secant line versus the of a vector value function. So just know that the definition from calculus 1, the limit of the difference quotient of the derivative, it applies to vector value functions as well. Because if we expand this out, then this would, turn into something like the limit as h approaches 0, f of t plus h minus f of t over h, so on and so forth with, g for the y component and h with the z component. So in each case, we do just the limit of the difference quotient with, for each component. And so that means all of the nice properties and all the derivatives that we know and love from calculus 1 still hold. They still hold. Same thing with integrals too. So like the integral from a to b of a vector value function, r of t, is going to be the integral from a to b of f of t, the integral from a to b, g of t, and the integral from a to b of h of t. So integrals, still like we know and love, same integration techniques. So let's start with an example. Let's see, example. Sketch the vector equation. Find r prime of t. And then sketch position vector and tangent vector. And our vector value function, r of t, is equal to e to the t I plus e to the negative t j. And at the point, or at time t equals 0. So this, you can see this lives in R2 because we only have the x and y component. This is in the xy plane. And so graphing this boy, here's what we can do. We can make a table. We do t, we do r of t. Right, we just -2, -1, 0, 1, 2. What do we get? We get e to the -2, e to the 2. Right, that's the point. And then we get e to the -1, e to the 1. we get e to the 0 is just 1, e to the negative 0 is also 1, and then we get the flip, e to the first, e to the negative 1, e squared, e to the negative 2. All right. So in plotting these points, we have 1, 1. That's the easy one. Okay, so now we have e to the first and 1 over e at time. This is t equals 0. So time t equals 1. We're traveling this direction, and then we get right 1, 1, 2, 2.7. Right, e is about right here, 2.71. And then we get 1 over e. You know, that's some fraction, so it's just going to be less than 1. So this we get some asymptotic behavior because e squared we get mapped to, you know, it's time t equals 2. We get mapped, you know, even further along the x-axis and even closer. But you notice that the y component will always be greater than 0 because it's exponential. So we have really this is the graph of 1 over x. In the first quadrant. Okay. So we sketched the vector equation. Now we have to find r prime of t. If r of t is e to the t, e to the negative t, then r prime of t, well, the derivative of the first component, e to the t, is just e to the t. The derivative of the second component is what? Negative e to the negative t from the chain rule. So negative e to the negative t. Okay. So that's r prime of t. You sketch the position vector and tangent vector at time t equals 0. So r of 0 was, we said, 1, 1. And then r prime of 0 is equal to, let's see, this is e to the 0, negative e to the 0. We get 1, negative 1. Okay. So sketching the position vector that always comes out from the origin. It points from the origin to the point of interest. So the position will look like this. It points to the point 1, 1. And now the tangent vector, that's actually tangent to the curve. And it's going to have, you notice it would have the same magnitude as the position vector, but it's going in a different direction. We go starting at the point of tangency. We go to the right one, down one. This is what it would look like. Okay. So what we just found, if r of t is position, what is r prime of t? Does anybody know? If r of t is position, r with respect to time is velocity. And then r double prime of t is acceleration. What about r triple prime? What do we call that one? Does anybody know what we call r triple prime? R triple prime of t is actually called something called, it's a jerk. Jerk, believe it or not. So can you guys hear me? Never heard of that before? Okay, cool. Yeah, it's jerk. Cool, sweet. Yeah. So it's the unit associated. If this is meters per second, this would be meters per second cubed. per second, how you're changing. Okay, so now we have another example. This time is in R3, and we are asked to see, we're given 2 cylinders. And we want the equation of the tangent line to the curve of intersection of these cylinders at this point. So at the point 3, 4, 2, we want the equation of the tangent line of the curve of intersection of these cylinders. So to find an equation for the curve of intersection of these cylinders, what do we need to do? Right, these are vector value functions, so we want a parameter. It's called a parameterization of the curve of intersection. So we want r of t, and we want some function x of t, y of t, z of t that would model the curve of intersection of these two guys. So does anybody know where we would start with this? Any ideas? Yep, that's it. Yeah, I usually pick x because, I mean, that's usually the independent variable. So yeah, I'd picked, x equals t, and then we solve y as a function of x, and then plug in t, and then we solve z as a function of y, and then plug in our parameterization y, and then we'll be good. So yeah, if x is equal to t, then we have, well, solving the first equation, x squared plus y squared equals 25 for y, we get y is equal to, well, plus or minus, right? We have plus or minus the square root of 25 minus x squared. I'm going to pick the positive because notice with our point, it's positive. So now we have a function y of t equals the square root 25 minus t squared. Boom, we have 2 of them already. Now for the third one, we solve z for y. That would be plus or minus the square root of 20 minus y squared. We pick the positive, and now we plug in our function y of t. So we get z of t equals the square root of 20 minus, well, then we plug in the square root of 25 minus t squared. But notice we're squaring it right here. So the square root's going to go away. We get minus 25 minus t squared. This is equal to the square root of, distributing and adding everything. We get, positive t squared. We get 20 minus 25 is negative 5. And our vector value function of the curve of intersection is t square root 25 minus t squared square root t squared minus 5. And this would only give you the positive side of the curve of intersection. All right, so we want the equation of the tangent line at the point 3, 4, 2. So what what t value makes happen, right? Well, obviously x is t, so we have to have x match up with x. This point happens at t equals 3, and so we're going to take the derivative r prime of t, and then we plug 3, and then we just plug it into parameterization of a line in space. So yeah, r prime of t, well, the derivative of t is 1. The derivative of square root of 25 minus t squared, let's see, we get 1/2 25 minus t squared to the negative 1/2 times 2t, simplified later. And derivative right here, we get 1/2. That's a negative, isn't it? Negative 2. Is 1/2 t squared minus 5, negative 1/2 times 2t. So we get 1. The 2 cancels. So we get negative t over the square root of 25 minus t squared. And then we get the 2's cancel. We get t over the square root of t squared minus 5. And then we evaluate at the point t equals 3. So we get 1, let's see, negative 3 divided by, we get 25 minus 3 squared in the denominator under the radical. That's 25 minus 9, which is really just 16, but the square root of 16 is 4. And then we have 3 over, this is a 5. Let's see, 9 minus 5 is 4, square root of 4 is 2. Okay. So this is the vector parallel to the tangent line, the tangent line of interest. This is the vector parallel to it, the slope vector. Now, remember, we can use any scaling of this vector. I don't want to deal with fractions. I'm going to multiply this vector by 4. So we have 4r prime of t is still a valid vector to use for our tangent line. We get 4, negative 3, and then that would be 6. Okay. Plugging it into the equation, we get L of t is equal to, initial point was 3, 4, 2, and plus time times 4, negative 3, 6. And then you can add the two vectors, or you just leave it like this. That's fine. Okay. Yeah, this next problem ain't nothing really to it. There's it's just a little bit of, I guess, a Cal 2 review, right? It's asking for the integral of secant squared t I plus t squared plus 1 j plus t squared ln t k dt. Right, because all it's really, this problem is 3 single variable integrals. So tell me, what is the integral of secant squared t? Anybody? Well, remember, the derivative of tangent, yeah, is secant squared. So then the integral of secant squared is tangent. So we have tangent I, and then how do we integrate this? What? Yeah, see, that's why I brought it up, That's why I was really just testing y'all. But what technique of integration do I use here? How do I integrate U sub, that's U sub, because we have the integral t squared plus 1 dt. Look, this, we set for U, and then, notice the t right here is 1 power lower. And so when I find my du, well, my du is obviously going to be 1 power lower because I take a derivative. And then I can solve for t dt. We get du over 2 is equal to t dt. And so this integral is really u du over 2. Okay, well, the integral of u to the first is u squared over 2. So we get u squared over 2 times 2 is 4. And then we plug in u, and then we get t squared plus 1 squared over 4. And this is the j component. Yeah. I actually wrote that down wrong, but it still worked out. It was actually to the third. But it would be the same sort of solving. Oops. If we put the third right here, what would happen? Well, it would be the same u that works, same du, and this would just be to the third now, and then we would get plus 1, 4, and so we would get an 8 right here, a 4, and an 8. So, oops, little just copied it down wrong. J. Okay. Now, how do we integrate t squared ln of t? What method of integration, what technique of integration do we use? Yep, it's integration. And so with integration by parts, remember, we pick a u, and then the remaining is dv. And there's an order of choosing u, ilate. Inverse trig, logs, algebraic, trig, exponential. That's order precedence for picking u. So we have a log for algebraic right here. So we're going to pick u to be ln of t. Du would be 1 over t dt. dv is just what's remaining, which is t squared dt. And then we have v would be, well, the integral of that is just t cubed over 3. Then we have the formula. Integration by parts is uv minus the integral of v du. So we have u, which is of t, v, t cubed over 3, minus the integral of v du, well, minus the integral of t cubed over 3 times 1 over t dt. Well, this is just, t cubed divided by t. This is t squared now. And we integrate that, well, that's just, t cubed over 9, and copy and paste the rest. And so this is my k component. So we have t cubed over 3 ln t minus t cubed over 9 k. And then, putting it all together, you would have to have an integration right here. Here's my x, here's my y, and here's my z. And then you would add plus vector c at the very end, where vector c is equal to something like c1, c2, c3. All right. We have another example. Okay, where's my, yeah, find the point on the curve r of t equals 2 cosine t, 2 sine t, e to the t. T is in between 0 and pi. What is this curve called? Find the point on the curve where the tangent line is parallel to the plane square root of 3x plus y equals 1. What is this vector value function called? We have a cosine, we have a sine, and we have an exponential. It's a helix. Well, it's kind of a helix, right? We got the circular motion going along in the x and y. So we're going to be, contained on a circle around the z-axis. Yeah. It's a helix, right? But so it is contained on a cylinder for sure. It's contained on the cylinder with, it would be radius 2. Radius 2. And then the only difference, normally with a helix, we just have t or some like 4t or something, some constant times t. But this is just e to the t. All that means is that this helix, the growth of it is exponential. It grows extremely quick. It just goes up faster than a normal helix would. So that's the only difference, right? If it's a cosine and a sine, and then something, just, is monotonically increasing, then it's a helix. Cool. So I'm going to graph this plane real quick. All right, so if we solve this for y equals negative root 3 x plus 1, we have a y-intercept of 1. X-intercept of, let's see, set y to be 0, subtract, divide, 1 over root 3. So, I mean, somewhere right here, positive x-axis. And then we just connect it. So this would be the line in R2. And then extending it to R3 is just parallel, to Z, because Z. I got some echo. That was really weird. Okay. So there's Z involved. So anyways, yeah. So the normal vector to this plane is what? Right, it's a plane, so it has a normal vector in anybody? So the normal vector to a plane is always the coefficients of x, y, and z. So the coefficients of x, y, and z in this case are square root of 3, 1, and 0. Okay. So we want to find the point on this plane. It's parallel to the plane. Then that means it's orthogonal to the normal vector. Yeah, the lack of z, that means z is 0. Yeah. we have no rise. Look at this normal vector right here. Look at this guy. Observe. These are some glasses. Look at him. Yeah, he's parallel to the xy plane. He has no rise or descent, so he is the z component. Yeah. So yeah, if we're tangent line parallel to the plane, this means orthogonal to n. Orthogonal to the plane, parallel to the plane, so we're orthogonal to n. So now what we do is we just take a derivative of our helix. R prime of t is equal to, and what do we get? We get -2 sine t. The derivative of 2 sine t is 2 cosine t. Derivative of e to the t is just e to the t. Okay? And so we're going to take this guy, we're going to take equation, this derivative, we dot product with the normal vector, and it's equal to 0 because we're orthogonal. I'll always fall back on the dot product being 0. That's just yeah. Thank you for telling me that. I didn't know. Can you see it? Can you see it now? Yeah, we're good. Cool, sweet. So, let me know if that happens again. So yeah, we product with normal vector. Have an equation, and then we just solve. So r product in -2 sine t, 2 cosine t, e to the t, dot product, square root of 3, 1, 0. Oh, cool. I'm glad there's a 0 right here because that eliminates my e to the t. Yep. Sorry, guys. All right, so I changed my, I'm now connected to my personal hotspot, and I think this should be better. Can you guys see the screen all right? Cool. I guess next week I'll probably just go up to campus and use their Wi-Fi because my Wi-Fi's been pretty spotty. Anyways, let's see. Yeah. I don't know where you guys left off, but we were solving this dot product equation equals 0. The derivative r prime of t dot 0, and then the e to the t cancels with the 0, and then we get 2 cosine t negative 2 square root of 3 sine t. And now we're just solving for t. We come to this equation. Cosine t equals square root of 3 sine t. Where is that true? For what values of t does that hold? And remember, t is greater than 0 and less than pi. You have to know your trigonometry. Let's go back to the unit circle. It's pi over 6. Yeah. Because if we do pi over 6, we have square root of 3 over 2, 1/2. So that would be cosine of square root of 3 over 2 equals square root of 3 times 1/2. Boom, those are equal. So at t equals pi over 6, we have that the equation of the tangent line is parallel to the plane. We don't even have to find the tangent line. We just have to find where the tangent line is parallel. So now we take pi over 6 and plug it into r of t. So r of t, well, this would be 2 cosine of t, 2 sine of t, e to the t. So it happens at r of pi over 6. So this is square root of 3, 1 e to the pi over 6. Cool. Now I have a more theoretical question for y'all. I thought this was a pretty interesting problem. So we have r of t. This is, suppose r of t is orthogonal to r prime of t for all t. Show the curve lies on a sphere with center the origin. R of t is orthogonal to the derivative of r. That's the only information we're given. Show the curve lies on a sphere with center the origin. How do I solve this? Any ideas? How do I prove this? What should I do with this statement? Orthogonal? Two vectors are cross product. Let's see. Well, okay, so r of t and r prime of t are already orthogonal. So if I took the cross product of these two, I would get a new vector that's orthogonal to both of these. So then I would have 3 orthogonal vectors. So that's not quite the route to go with it. Think dot product. What theorem involves the dot product and orthogonality? Dot product equals 0. Yep. So we have r of t dot product with r prime of t equals 0. Okay. Now, this is in R3 because we were talking about a sphere, right? So this R of t is in R3. So that means we're going to have an x component, a y component, and a z component. And we're dot product with x prime of t, y prime of t, and z prime of t equals to 0. Just, do the dot product, do the operation. So we have, x of t, x prime of t, plus y of t times y prime of t, plus z of t times z prime of t, still equals 0. Okay, well, now I have a derivative mixed with my, position vector equations. So I want to integrate. I'm going to integrate the left-hand side and the right-hand side of this equation. So I'm going to integrate here with respect to t, integrate here with respect to t. Well, on the right-hand side, the integral of 0 is just a constant, some c. And then how do I integrate? Let's just examine the first one for right now. How do I integrate x of t, x prime of t dt? Any ideas? Suppose, x of t is known. And x prime of t. You sub, let me think. Yeah. Perfect. So u equals x of t, du equals x prime of t dt. So then we get, the integral of u du. So this is just u squared over 2 plus c, but the plus c would get absorbed over here. And so this is going to be for each one. We have x of t squared over 2 for the first one. We have plus y of t squared over 2 plus z of t squared over 2 is equal to c. Multiply the 2 across. We have, really, it's just x squared plus y squared plus z squared equals 2c, so I would just call it c1. That's a sphere. That's a sphere. The x component squared plus the y component squared plus the z component squared equals some constant. By definition, is standard form of a sphere. So we have showed it. Done. And guys, I learn something from you every week. When I worked this problem, I went to the trouble of when I integrated this, I did integration by parts. But you just showed me u sub. That was so much easier. So good job, y'all. Both of y'all got that one. Okay. So that was the theoretical question. Now we're going to talk about arc length. I noticed, I was looking at you guys' PLTL problems. You had a lot of arc length problems on there. So I would assume it's going to be, tested heavy over or something to that effect. I don't know for sure, but it just seemed like there was a lot of problems. So arc length, as we know, L is equal to, here's our formula, the integral from A to B, the magnitude of R prime of t dt. So that is if R of t equals x of t, y of t, z of t, then R prime of t equals x prime, y prime, z prime, and then we get the magnitude of this vector. Well, that's just, the square root of each component squared. And so we just integrate that with respect to t, and that'll give us the arc length of a curve. So let's do an example. We have R of t equals I hat plus t squared j hat plus t cubed k hat, and we want the length between 0 and 1. Okay, so first I calculate R prime of t. I get, well, the derivative of 1 is just 0. Then we have 2t. Then we have 3t squared. Magnitude of this guy. Well, this is the square root of 0 squared plus 2t squared plus 3t squared squared. So this is going to be the square root of 4t squared plus 9t to the 4th. But look what I can factor out. Look what I can factor out. I can factor out a t squared. So I have t squared, 4 plus 9t squared. Okay, so the square root of t squared is just, absolute value of t, square root 9t squared plus 4. Okay. Since t is positive, we can drop the absolute value. So really, we're just integrating 0 to 1, t square root 9t squared plus 4 dt. Okay. Let's see. I have a lot more stuff I want to get to, and I'm going to leave you guys. You can solve this integral. First, what technique of integration would you use? Tell me. U sub, yeah. Yep. Both of y'all, very good. Yeah, because we see it's the power in the interior is 1 greater than the power outside. So then we can use U sub. And then I'll give you the answer. The answer is over 27, 13 to the 3 over 2 minus 8. All right, let's do another arc length. We might actually solve this one entirely just because it's some integration you guys might have forgotten. Let's see. Okay, so we have R of t equals cosine of t, sine t, ln cosine t. And we want the arc length from 0 to pi over 4. So the first thing I do, just take derivative. So that's going to be negative sine t cosine t. And what's the derivative of ln cosine t? Remember, the derivative of ln of u, if we want to dx this, we get u prime over u. So we get the interior. So cosine goes on the bottom, and then the derivative of cosine goes on top. So that's going to be negative sine. Oh, look, that's actually negative tangent. Cool. So we have negative sine, cosine, negative tangent as the derivative. we take the magnitude. This is going to be the square root of sine squared t, cosine squared t, plus tangent squared t. Well, sine squared plus cosine squared is just 1. 1 plus tangent squared t. Well, 1 plus tangent squared t is really the same thing as secant squared t. So we have the square root secant squared t. This is absolute value of secant of t. But, you know, t is positive and secant's positive on this. This is what secant looks like from 0 to pi over 2. So we're really doing it from here to here. We have positive, we have above the x-axis, so we don't need to worry about the absolute value sign. So we're just going to integrate 0 pi over 4 secant t dt. What's the integral of secant of t? Does anybody know? That's it. ln absolute value secant of t plus tangent of t. Evaluated from 0 to pi over 4. Okay, so we get ln secant of pi over 4 is really 1 over square root of 2 over 2. 2 over square root of 2. Rationalize the denominator. We get 2 square root of 2 over 2. These cancel. This is square root of 2. Secant of pi over 4 is square root of 2. Tangent of pi over 4 is just 1. And we subtract off ln secant of 0 is 1. Tangent of 0 is 0. This term goes away. So the answer is ln square root of 2 plus 1. Some trig identities and some trig integrals, but it's all in good fun. So let's go on to the next one. This is kind of more of a conceptual problem, but you still work with the formula. Let's see. All right. So suppose you start at the point 0, 0, 3 and move 5 units along the curve. We have the curve 3 sine t, 4 t, 3 cosine t in the positive direction. And now it's asking you now. So first of all, what is this? What is the shape of this curve? The shape of this curve, another helix. Yep, they come up a whole lot. Yeah, this one is about, I think you both said something. Yeah, both of y'all got it. Very good. So it's about the y-axis this time. So, you know, you have your y-axis, and then the helix is traveling about, you know, this guy. So, and this is y. Or just stretches it a little bit. Okay. So at t equals 0, we have 3 sine of 0, 4 times 0, 3 cosine of 0. So at t equals 0, we're at our starting point, 0, 0, 3. Okay? So if we move 5 units along the curve in the positive direction, and it's asking us where we are now, we're really looking for a t value. So what we're going to do is we're going to integrate from 0, because that's the starting point, to b. We're going to do our arc length formula because we were traveling along the curve. And we set it equal to 5 because that's the distance we want to go. And then we just solve for b. So r prime of t is going to be 3 cosine t, 4 negative 3 sine t. Magnitude of r prime is equal to square root 9 cosine squared t plus 16 plus 9 sine squared t. 9 cosine squared t plus 9 sine squared t is really just 9. Then we're adding 16 to that, so that's root 25, which is just 5. That's what my integrand is. That's the interior. So we have the integral from 0 to b of 5 dt equals 5. So this is going to be 5t evaluated from 0 to b is equal to 5. We have 5b minus 5 times 0 is just 0 is equal to 5. And divide by 5, b is equal to 1. That's the time at which we have traveled 5 units along our curve. So the point that we're at is we just r of 1, which is 3 sine of 1, 4, 3 cosine of 1, based on our equation right here. We just plug in 1 for t, and then we're good. So that's the point at which we have traveled 5 units along the curve if we start at 0, 0, 3. All right. So I'm not really going to talk about section 14.1. What is in that section is functions of several variables. There's no calculus involved with it. You just do contour maps, contour drawings of these functions of multiple variables, 2 variables, and then you also try to like identify, match up what the picture would look like from the equation, right? What the graph of the function of multiple variables would look like. So really, right? I mean, I'm gonna be really mathy with y'all right now. So before in chapter 13, we had functions R that mapped, let's see, 1 variable to 3 variables. So this was all the functions. This was the type of functions we were dealing with this whole time. Like everything previous to where I wrote this is the type of function we were dealing with. We map from R, that's the t, and then we map to a point in R3. Okay. And so these new functions that we're going to be dealing with in chapter 14, functions of several variables, we're going to have f maps R2 or more to R. So when you map R2 to R, this special case, so R2 is the XY plane. So we have like a 3-dimensional drawing. My domain is potentially, this whole entire plane. And then we map to a z value. And that's the output. So we have a point on the XY plane, and then we go up some height, and then that's our output of our function. Okay, same thing. We could really go, f maps R3 to R. We wouldn't have any way to geometrically interpret that because we would need 4 dimensions, but the idea still holds, right? These are functions of several variables, and so we're going to talk about something called partial derivatives. When you have a function of several variables, you have to take partial derivatives. So in general, we're dealing with functions that map Rn to R. Rn just means like an n tuple, x1, x2, all the way up to xn, and one real number as the output. Whereas before, you had one real number as the input and 3 real numbers as the output. So we could identify, just a curve in space. These are more, these are different now. These are multiple inputs, one output. Okay. Quadric surfaces, perfect prime example of a function of multiple variables. Right, if we have the paraboloid f of xy equals x squared plus y squared, well, this is f maps R2 to R. We get a scalar output with 2 real inputs. So it's a function of multiple variables. Okay, so I'm going to give you guys a definition. If f is a function of 2 variables, its partial derivatives are f sub x and f sub y defined by, and here's the definition. What's the definition of a derivative in a single variable? The limit of a difference quotient. So what we're going to have now is the definition of a partial derivative. It's still the limit of a difference quotient, but here's how it looks. It's a function of 2 variables still, and it's equal to this. It's equal to the limit as h approaches 0 of f of x plus h comma y minus f of xy divided by h. If we have a function of 2 variables, we will have 2 partial derivatives. This is one of them. The second one, f sub y of xy is equal to the limit h approaches 0. Can you guess? I just don't put it with the x. I put it with the y now. F of x, y plus h minus f of xy divided by h. So what this is saying is I just take, in the first equation, I just take a small step in the x direction and watch what the output is. In the second equation is I take a small step h in the y direction and I see what the output is. I see what the slope is, right? So yeah, if you have 2 variables, 2 partial derivatives, it's just looking at the change in x alone, looking at the change in y alone, and just leaving the other variable fixed. Some notation that you might run into, f sub x of xy, the partial derivative of f with respect to x is the partial derivative of f with respect to x, is the partial derivative of f with respect to x. That's not a 2, that's like a weird d. The partial derivative with respect to x of f of xy, the partial derivative of z with respect to x, f1, d1f, dxf. These are all the same thing. You'll see these 2 most commonly used. For y, it's the same deal. There's a lot of different notations, yeah. The book listed all of them, and I think it's good to know them. You really use these last three a whole lot. You see this if you do like upper level, some upper level math classes. You'll see this one in this class. You'll see this one for sure. You'll see this one. You'll see this one, and you see this one already. And so the partial derivative of f with respect to y of xy is the partial derivative of f with respect to y. Partial derivative of f with respect to y. The partial with respect to y of f of x. The partial of z with respect to y, f2, d2f, dyf. Okay, so as far as calculation of these things go, it's really not that hard. So if you want to calculate f sub x, here's what you do. Here's the rule you follow. Regard y as a constant and differentiate 8 with respect to x. F sub y calculation. Regard x as a constant and differentiate with respect to y. Example. F maps R2 into R, given by f of xy is equal to x to the fourth y cubed plus 8x squared y. Calculate f sub x of xy, f sub y of xy. Okay. So we have two terms, right? We have this term, this term. Let's work on f sub x first. The partial derivative of f with respect to x is I treat y as a constant. If y is a constant and it's being multiplied by x, it's like saying the derivative of 2 times x to the fourth. So y will just tag along. And I just differentiate x to the fourth. What is the derivative of x to the fourth? Regular derivative. Yep, 4x cubed. We treat y as a constant multiple, so it just hangs on. And then for this term, we differentiate x squared, and we treat 8 obviously as a constant, but also the y as a constant. So we get plus 16x, yeah, very good, 16xy. What about fy? Tell me fy. Perfect. Yep, we have 3x to the fourth y squared plus, this is y to the first, so the derivative of y to the first would just go to the constant term. We treat x as a constant, so this is plus 8x squared. All right. And one thing that's also is we can have secant partials. If we have a function of 2 variables, then we're going to have 4 secant partials. We're going to have f with respect to x, then with respect to x. We're going to have f with respect to y, then respect to y. We're going to have f with respect to x, then with respect to y, And then we're going to have the opposite of that, f with respect to y, then respect to x. So let's calculate these two in particular. So let's take f sub x and then differentiate with respect to y. So take this dude right here, this guy, differentiate with respect to y. What do we get? (12x cubed y squared plus 16). Yep. We get 12x cubed y squared plus 16x. What about f sub yx? Take f sub y, differentiate with respect to x. Same thing. One last thing. Called Clairaut's theorem. So suppose f is differentiable. Is defined on a disk D subset of R2 that contains the point AB. If f sub xy and f sub ys are both continuous on B, then f sub xy of AB equals f sub yx of AB, i.e. mixed partials are equal. And we just observed that right here. All right, guys. That's it for this session. I do have more material, but it's drawing close to the end of time. So, you guys have any questions while I'm here? Any questions? Yeah, great day. I'll see you guys later. Yeah, you're welcome. You're welcome. See you guys next week, hopefully.